piss off and what to say. The other one.
Can you hear me? All right. Thanks, Tim. Can you see it? Cool. And yeah, thank you, Tim. Thank you, PIXELvienna, and thank you, Victoria, for getting this whole thing together. Yeah. Oh yeah, just as a heads up, usually this presentation was crashing somewhere halfway through. I don't know why exactly, but yeah, just be prepared for that. So yeah, hi everyone. Today I'm going to talk about how to recreate Berlin's messed up sidewalks in Houdini. Well, it's not only about sidewalks, but I am going to use this tool as a case study to show you that wherever you look, there are patterns. And once you understand one of them, you will start seeing them all around you. The goal of this talk is to teach you how to recognize these patterns and then how to tell a computer how to recreate them. But before we get into this, a little bit about me. All right, hey, that's me. And that's also me. So my name's Julian. I'm a technical artist at Cloud Imperium Games. You might know us from our game Star Citizen. If you don't know it, shortly put, it's basically the most ambitious sci-fi game project ever, with 1,000 employees working on it worldwide. It's a crowdfunded online game that's been in development for over 13 years. I was a teenager when it started. The whole process is open for everyone to see, with the funding and spending laid out and explained to the players. If you're curious how we developed this game, there are interviews and presentations by our developers on the large and small changes that our game is going through over the years. My job as a technical artist is to assist the environment art departments with procedural tools made with Houdini. For instance, this destruction tool here. It's an awesome place to work. I'm learning so much since I joined. And shout out to the organics team in Frankfurt. Shout out to the props team in Manchester and the concept art team. They're amazing. And outside of my work at CIG, I'm also making tutorials with side effects. This is my wooden bridge generator for Project Skylark. This was my nasty flesh tool for Project Grot. And both Project Skylark and Project Grot are for free. You can just go on sideeffects.com and watch them. It's not just my tutorials, by the way. There's a ton more from other really talented people, you know, with rock generator tutorials, lava flow, a bunch of other stuff to make these scenes come to life, basically. And part of these projects, I'm also doing workshops. By the way, I'm doing a workshop later after the lunch break. So feel free, you know, if there's anything you like that you see here, you can ask me questions and I can show it to you in detail. Because this is going to be a bit more, you know, like high level. I'm just showing you pretty pictures. But over there, you can, you know, see how the tech works. I also write a tech art blog on ArtStation, where I break down previous projects and teach Houdini fundamentals, you know, if videos aren't your thing. Like for instance here, this flesh tool that I was showing, here's like a written down version of where I show how it works. This talk is going to have two parts. First, I'm going to do an introduction into what procedural art is and give some examples, you know, for those that don't know what it is. And then we are going to go through my journey of making the sidewalk tool that you see right here on screen and where it might go in the future. All right, so what is procedural art? This is always a difficult question for me to answer, especially, you know, when the person I'm talking to isn't in game development or something, like, you know, a relative. So maybe let's start with a little thought experiment first. Let's say we come across a tiled wall and we think it's awesome and we want to recreate it digitally using a procedural system. Before we can even get started on doing that, we need to consider a few things. Think about the individual tile. How is it created? What material is it made of? What glaze? What color? How shiny is it? Is it a rough, natural clay tile? Is it a fancy Portuguese tile with intricate artworks on it? Then let's think about the tiling pattern. How are they arranged? Simply one by one in a checker-like grid pattern? Is every second row offset by half? What if the individual tiles aren't even square-shaped, but they're like arranged, you know, like a herringbone pattern or something? How does the design of the individual tile contribute to the greater whole? You can already guess from these questions that even something as simple as a tiled wall can occur in many different shapes and sizes. And this is just us talking about the overall shape and layout pattern. What about dirt, weathering, damage? Glazed tiles can sometimes crack over time or during the firing process called crazing. It's this cool pattern here. I really like that. And if the tiles are outside, they will collect dirt over time as dust particles carried from the rain and air pollution deposits in convenient locations. But we can keep going. What if they get damaged? How do the cracks propagate? What if a tile falls out? What is behind it? Is there grout smeared across the surface and the tool marks created by the hand movements of the construction worker? This might sound like we're trying to recreate reality, and yes, that is exactly what we're having to think about as procedural artists. The more you know about the process behind whatever you're trying to recreate, the more convincing your end result is going to look, and the easier your work is going to be. And here's an example of one of these systems. Pay attention to these sliders that you see on the right there. These are called parameters, and they control the behavior of the system, such as the amount of damage you see me increasing and decreasing. But we can also control things such as the size, color, shininess of the tiles, the amount of dirt, any rule we can come up with, in fact. One definition for procedural or generative art I found to be very effective is from generative artist Philip Gallanter. He said, generative art refers to any practice where the artist uses a system, such as a set of natural language rules, a computer program, a machine, or other procedural invention, which is set into motion with some degree of autonomy, contributing to or resulting in a completed work of art. The key element in generative art is then the system to which the artist cedes partial or total subsequent control. Or, simply put, generative art or procedural art is about the interaction between an artist and a system. So, how is it used? We saw this one use case with the blue tiles, but let's look at some more examples. So let's say we want to make a hanging bridge 3D model. It's very complicated looking, right? So many parts, so many little pieces. Imagine making that by hand. How long would that take? Well, all right, now we've made it. But let's say we have to change it for some reason. You know, in games and movies, changes happen quite frequently. It's a regular thing. Let's say the story has changed and they're walking up steps next to a mountain instead of a hanging bridge. How long would that take? And another change, and another change, and another change. Or a different question, how willing would you be to accept a mediocre result because you didn't have time to make it look any better? There are so many other things you have to do, right? Like, this doesn't look like a mountain. What if you want to make it look like a realistic mountain? What if you want to build a house there too? And this is where procedural systems can be incredibly handy. What you see here is the procedural wooden bridge system I've made for SideFX's project Skylark. And you can see I can keep changing it and it will adapt. It can also, it's aware of the environment, and it will recalculate and give me a new result. This way of working is what we call non-destructive, meaning I can make changes at any point without having to start over or break what's already there. You might also notice that the colors look a bit weird, and that's what it looks like while I'm working on it. Each color is representing a certain system or a part of the system. The hanging bridge logic is orange, the regular walkways are green, and the blue parts are where the incline becomes too steep and it switches to staircases. There are dozens of smaller systems running in the background, as well as the tool, such as the tool's awareness of the surroundings, to, even if you look closely, there's like nails hammered into the planks. And this is what it looks like to the user, the artist. The complex logic behind this tool is hidden, and they only see a few sliders, like what you see on the right there. They can control things such as the hanging amount of the bridge, the width, whatever we want them to be able to control. And because usually these tools are created in close communication with the artists to make sure their needs are met. In my opinion, this is a good example for something that is so intricate and so detailed, you wouldn't really be able to do it by hand unless you have a lot of time. Now let's talk about the opposite scenario. Here's an example from Star Citizen. As you can see in this image of our game, there are a lot of asteroids, like too many to make by hand and too big. Some of them are several kilometers large, but still need to have enough detail to look convincing up close. One of these asteroids, Levski, is so big, like this hole that you're seeing right there could fit several skyscrapers. Like here, I hope you can see it. Like there's a spaceship in there that's like as big as a house. Like, pretty insane. Just to put this even more into perspective, in this incredibly detailed area, which was made by many of my colleagues from Frankfurt, UK, Montreal studios, you are about this big. Just so you get an idea of the scale and detail required. And the entire rock surface you see in the background was made by my colleague Lucas Chovanek, and not by hand, but by a procedural system that he made, an asteroid generator. I obviously can't explain how it works, but it can create asteroids of any size, and they look handmade. The tech is so cool, like I hope he does a talk about it someday. And as a little side note, procedural tech is not a new thing. This, for instance, is from Elite from 1984, so it's like 40 years old, and it already used procedural tech to make its planets. This circle thing is a planet. But not because they wanted a gazillion different planets to explore, but because it was literally more efficient to have a procedural system that generates them in the moment compared to storing them all in your computer's memory. All right, so how does it work? What kind of dark magic is behind all of this? At the heart of these procedural systems are instructions. Instructions we give the computer to fulfill a task the way we would do it. But what does that mean? How could I imagine these? Well, we're all familiar with at least one type of instructions. Recipes. Recipes are instructions, but for people, not for computers. They share a lot of similarities with how computers and procedural art works. You have a handful of inputs, the ingredients. You have your instructions, such as chop into bite-sized pieces, bake at 180 degrees for 30 minutes, and we have an output, your finished dish. The same raw ingredients can be processed in countless different ways to create countless different results. Sometimes we even have the same specific ingredients that are just being used in a different order, in different amounts, or being prepared in different ways. So in this food metaphor, a procedural system is the recipe, not the dish. And in the same way that you would write down and explain to someone how to recreate your special family recipe, we have to explicitly, step by step, explain to our computer what to do. And this is what these systems look like while we're working with them. What you see on screen is called a graph. Each of these individual squares in this graph is called a node. These are our instructions, such as move the 3D model to the center, cut a hole into this object, kind of like our recipes. But wait, how does this work? What is going on inside of one of these nodes? Basically, nodes are visual representations of code. Some of them can be quite simple, like adding two numbers together. Others can do a lot more. By combining these nodes, we can quickly create intricate patterns and effects. A great quote from Mandelbrot that sums this up is, "Bottomless wonders spring from simple rules repeated without end." But just like with cooking in real life, we can't just willy-nilly combine these things. I mean, we can, but then, the food would probably be unrecognizable and taste horrible. If we want our food to taste good, we'll have to follow certain rules. So let's talk about these rules. We live in a world of rules. Some are explicitly stated, such as the dimensions and building instructions of this IKEA shelf, or the standardization of public infrastructure. These are man-made rules with numerical values defined by a designer or governing body that you can easily look up on the internet. The German Institute for Standardization, Deutsches Institut für Normen, or DIN, for instance, dictates everything from the size of paper to the acceptable range of height for steps on staircases, which, by the way, is 17 to 19 centimeters. These rules are called DIN norm, and they are documents that define the requirements for certain products, services, and procedures. Fun fact, did you know that there's even a DIN norm for the design of DIN norm documents? It's DIN norm 820, look it up. One of the great things of procedural systems is that they allow us to make more of stuff. What do I mean by that? I mean, from looking at this thin paper graphic, we can kind of see how they all relate to each other, right? And we can intuitively imagine what the next biggest size is supposed to look like, because we kind of get the rule. In the same way, by understanding how this IKEA Kallax design works, we could imagine what it might look like in different sizes. This series of images in the background almost look like still frames from an animation, and I took the liberty to do that actually. And from looking at that, we can maybe even imagine what it would look like if it grew sideways, right? Or by looking at the sidewalk schematic for a little bit, I could imagine what should happen visually if the sidewalk would expand to the left or the right. This is kind of how procedural systems work. But not every rule is an explicit number on a document, waiting to be copy-pasted into your algorithm. There are other much more vague rules out there, not made by man, but by nature. The angles between each leaf of a plant, the erosion of mountains, or the movement of rivers, to name a few. These rules are guided by physical processes that don't have any written down rules, but require reverse engineering on our end to understand them. Some of them require observation over long periods of time and complex math to recreate them. We have entire scientific fields dedicated to solving just one of these phenomena. They are also much harder to reproduce faithfully, as we always have to accept a certain level of abstraction. To reproduce these organic physical processes, we can either fake it or simulate it, which is a very fancy way to fake it using math. Don't misunderstand me, these simulations are incredibly useful, even necessary for our society to function, such as weather predictions or something. And they often come astonishingly close to the real thing, but they're still abstractions. The more powerful our computers become, the closer we get to closing that gap. But it might also be that there will forever be a sliver of abstraction, as we are trying to recreate something analog, which has infinite detail, using digital means. Maybe a future version of computers we cannot even comprehend at this time will be able to fully simulate our world. Until then, we have to settle for good enough. But no matter if I want to recreate something man-made or something organic, there's one advice from Anastasia Opara I take to heart. Don't mimic the outcome, mimic the underlying phenomena that will get you to the outcome. This was from her 2017 SIGGRAPH talk, Believability in Procedural Art, which I highly recommend you to check out should you be interested in this topic after this talk. What she was describing was this tendency of people to view the world as static snapshots, when it's actually the accumulated end result of countless interacting systems. If we want to recreate believable procedural systems, we have to understand the system we're trying to recreate. And the key to understanding a system is understanding its behavior, and its behavior is guided by its rules. If you want to recreate mountains, it helps if you understand a little bit how erosion works. If you're trying to recreate a sidewalk, it helps to understand the labor a construction worker has to go through to build that sidewalk, as well as the actual rules that they have to follow on the job. So, to sum it up, procedural systems allow us to create things that are incredibly big or detailed, or both. They can be aware of their surroundings and adapt to them. And the key to unlocking this potential lies in understanding the rules of the thing you're trying to recreate. The better you're able to recognize and translate them, the more convincing your end result is going to look. All right, now comes the real thing. Now that we sort of understand what these systems are and how they work, how do we use this knowledge to recreate something like Berlin sidewalks? Well, since I used recipes as a metaphor, I will first tell you my life story before telling you how it works. Well, just kidding. But let me tell you how this project came to be. So this project started 6 years ago, actually. At this time, I was living in Berlin and working at some archivist company. We were working on a project where we were recreating Berlin in the 1920s in VR. And as part of that, we, of course, had to faithfully recreate the pavement of the time period with all its details. Back then, I didn't know that much about procedural art. I knew Substance Designer, which can make procedural textures, like those blue tiles I've shown you earlier. But these textures weren't aware of their surroundings. They wouldn't be able to, draw these cobblestone borders right here. So I had to painfully make those cobblestone borders by hand. And as I was making those, I felt certain that there had to be a better way, but I just didn't know how. But the project was done and I was off to other things, namely kitchens. Our company was working on an IKEA-style kitchen planner for some real estate company. Same idea. You click through different settings and the kitchen on the website would update, looks cool, blah, blah, blah. The website looked, easy to use and slick, but the creation process was far from it. Each individual combination of settings, something like 36 different possibilities, had to be modeled by hand by one of our interns under a grueling deadline. As if that wasn't enough, yeah, some here can relate to that. As if that wasn't enough, shortly after she submitted her work, the client came back with a correction along the lines of, could we maybe move all the handles to the left? Which, means 36 manual changes to be delivered as soon as possible. This is no way to work, I thought. This is not labor that should be done by a person. Nobody should do this. Nobody wants to do this. This experience, plus my own experiences, gave me the final push I needed, and it gave me a clear goal: building a kitchen generator. For the next 6 months, I would watch Houdini tutorials on procedural modeling after work and teach myself enough to create a bare-bones kitchen generator prototype that I could show to my boss. I made this really crude screen recording of it to convince him to let me research this technology at work, and to my surprise, it worked. I'm not exaggerating when I'm saying that this 30-second GIF changed my life. And this is the actual GIF, by the way. A few months later, I was able to hire my friend Dennis Brunn, and together we turned this crappy prototype into a really cool tool we dubbed Kitchen Generator. And here you can see it in action. It's still a pretty early version. It has developed much more since then, but it could already do a couple different design types and of course, generate UVs and some other things. So anyway, now I know Houdini. But to be honest, I didn't really care about kitchens, and the sidewalks were still there every day on my way to work, mocking me with their presence. But maybe with my newfound knowledge, I would be able to solve that problem. But where to begin? How do we make sense of this mess? Like with any art project, the first step is always to gather references, ideally from real life. Here are some examples of the many, many reference pictures I took. I think there's like 300 pictures of sidewalks on my phone. Starting from the left, we have the bishop's hat, which is I would say, the most iconic element of Berlin's pavements. Then in the middle, we have the cobblestones. And then on the right, we have these fat granite slabs, also called Schweinebäuche, pig's bellies. I will be going over those one by one in a moment, but before I jump into my software of choice, I usually do something else first. Sketching, yes. This might sound a bit strange, right? Drawing on paper when we're talking about systems and code and whatever. But there's a reason for it. To translate something you're seeing in real life to a digital system, we need to learn its rules. And we need to take the thing out of its environment and abstract its pure essence, its behavior. The best way I have learned from myself to do that is to draw it. A plant, material, building, doesn't matter. I will try to draw it in different scenarios. Like for instance, what if there was a tree in the middle of my sidewalk? How would it have to adapt? By doing that, we force our brain to come up with rules. These drawings, oh my god, that looks horrible. These drawings can be as crude or as detailed as you need them to be. I believe that even the act of picking up a pen is sometimes enough to trigger this process. In our head, we start to isolate, abstract, identify, simulate, and recreate. While I'm drawing, I'm starting to understand what the rules are. I make notes, putting these rules into words, giving them a name. They are vague directions, not commandments, and they will guide me through my creation process. All right, now we can finally get started. So, like I said, bishop's hat. That's the most iconic one. Let's start with that one. So in this reference image, we can get a pretty good idea of how these tiles operate. The majority of the surface is covered in diamond-shaped tiles with pentagonal shapes on the borders. In areas where there are obstacles, such as these drains, the pavement has to adapt, and the diamond tiles get replaced with other tiles that are cut to somehow fit in. After taking a closer look at these bishop's hat tiles, I noticed that they were arranged in an offset pattern, and with one tile being 50 centimeters wide, and each second row being offset by half, as you can see with the green and blue tiles. So I needed to make a tile generator, but one that is aware of its surroundings and can adapt when it needs to. It took a couple attempts, and what I've ended up with kind of surprised me. Voronoi. My search led me to Voronoi diagrams. Looks cool, right? But what are they? Voronoi diagrams are a way of dividing space into segments that are close to each other. Each of these colored segments are called cells, and the way you can imagine how they work, like with this cool animation from Wikipedia, is that we have a couple of points and they start growing outwards to infinity. And where two of the cells meet, they form a border. And they, by the way, Voronoi diagrams have a surprising amount of use cases from biology, mathematics, astrophysics, and like 10 more. It's crazy. For us in game development, for instance, it's often used to cut things, like with the destruction thing I've shown you earlier. Well, and one important quality that Voronoi diagrams possess is that the point, like if the points are arranged like in the video here, if the points are arranged in a regular fashion, so will the output, the shape that they produce. So I was wondering if I could use these Voronoi diagrams to make these diamond-shaped bishop's hat tiles. Like in my reference picture, I placed a point where the center of each tile would be. I colored one set of points in green and one in blue, representing the offset pattern I described earlier. And this is what I got. Hope you can see it, yeah. This is what I got from putting them into a Voronoi diagram, exactly what I was looking for. And the great thing about Voronoi is that since the outermost points keep growing to infinity, our outermost tiles can adapt to whatever shape we throw at it. And I mean every shape. There's a lot more to it, of course, but this is what lies at the heart of the system, points and Voronoi. All right, now to the cobblestones. How do these work? As I mentioned earlier, the main thing everyone notices is this iconic border, right? So we need to take care of that. I did that by taking the shape I want to fill and adding points to it, and then pushing them in to create a strip of stones. The gap between the points defines the width of the border stones. And that worked pretty well. And it was very quick to set up, but it had one major design flaw. Since I'm pushing the shape inward from the border, it resulted in these cornerstones that are always split. And in the real thing, they're supposed to be like that, where it says good. That's how it's supposed to be. So how do we fix that? I solved that in a really convoluted way by adding a spline in the middle of the strip and using that in another Voronoi diagram. Since Voronoi diagrams always grow outwards from the points, from the starting points, I basically that way get the same strip, but I shifted them by half a stone so that we have the stones at the border. You can see it in the end there. Come on. Yeah. And since I was on that whole Voronoi train, I thought, why don't I do the whole thing that way? So basically, I slice whatever mesh comes in twice, horizontally and vertically, to get these rows and columns that I need, and add some noise to it to give it a slightly, more random and organic feel. And that's what it looks like in the end. Let's play it one more time so we can see it. Oh man, I should have done that faster. Yeah. All right. The cool thing is, since Voronoi doesn't really care about the shape, I can even let the user draw it freely. Like here you can see I'm just basically, drawing a spline and it does its thing. All right, that only leaves our granite slabs. How do those work? As I mentioned earlier, the main, whoops, I forgot the note, sorry, I'm so sorry. What I wanted to say is the granite slabs are something a little bit different. Just kidding, I also made those using Voronoi. But one thing that's neat about them is that you can stack them and they remember the order, like here. And here you can see how I did that using Voronoi. I basically use a spline and I have this shape and then I just cut them where the points are. And since it's all procedural, we can of course still change the size, the amount of slabs, whatever, at will. Like here you can see me stress testing it and seeing how many I can stack on top of each other. I haven't made it break so far. And you can see that all of them are changing at the same time. If I wanted to, I could even make them, individually be controlled individually, but I just was too lazy. Another important visual to nail when aiming to recreate Berlin sidewalks is the displacement. And by that I mean the many dents and bulges that you can find all around the city, often from roots pushing out the stones. How does that work? Here's a little demo so we can have something cool to look at. Yeah, like basically, you can just draw and then it will make it look like Neukölln. No, it's not that bad. It's not that bad. I'm just exaggerating here. The trick is we first calculate the sidewalk, all of it, on a flat plane, and then we project the end result onto a deformed plane. And then we get this. Let's have a look at this breakdown animation. So these are all these individual steps that are happening to make this work. Basically, the way it works is, when you saw me draw something, I'm drawing a spline that gets passed on to a system that adds thickness to it to make it kind of look like a root. And then it gets projected onto this pink mesh that's the soil. And then I get the tiles, and as I said, they get projected onto the soil layer, and then they get the orientation from that soil layer. To explain how that really works is a bit difficult and probably take me like 5 minutes. But basically, we can check for each stone where the nearest surface is facing and then make the stones look in that direction instead of where they are facing right now. And here's another example, just using one mesh. Like that's the same tech that's going on. We have this pink cone, and notice that as soon as it's above the plane, it snaps to the surface, and then it also starts to follow this really exaggerated bump. That's basically what's happening with the stones, but we just don't notice it. And these were some of the many little systems that are interacting with each other to make Berlin sidewalks, at least my interpretation of it. So I thought, wow, it's done. I can share my work and move on to other things. I posted my work to Instagram, and to my surprise, people really, really like sidewalks. Especially this one. Yeah, it's crazy. It's really crazy. I mean, the reception was insane. I have never experienced anything like it. That was crazy. And the funny thing is, when you have a lot of eyeballs on your work, chances are somebody is going to notice your mistakes. But the fascinating thing about this at the same time was that because there were so many people watching, my work for the first time left my usual bubble of game developers and technical artists, and I had actual construction workers in my comments giving me feedback. Like this person, like correctly pointing out that the arrangement of my stones was wrong. So I looked into this Berliner Passe and saw what the deal is. And I found actual guidelines and educational material for, actual construction workers, the real rules that they have to follow on the job. And everything I thought I knew about cobblestones was shattered. The difference becomes really apparent when you put them next to each other. First, the center should be at 45 degrees, which mine aren't, they're just random. Second, the stones should try to follow the border. And third, these lines are forbidden. They're only allowed to have I think 5 stones max, and then you're supposed to break that line. And by the way, one thing that I found really cool was that this type of pattern is called, this type of pattern is called geordneter Wildverband, which roughly translates to controlled random band, a bond, which I think is really beautiful and kind of describes procedural art as a whole, controlled chaos. So how could I recreate that? At first I was convinced that I wouldn't be able to, but after looking at it for a while, I started to see the pattern, and I started to understand it a bit better. In the middle, the stones should be 45 degrees. On the border, they should align. And in between, they try to fit in somehow. So this is my first attempt at recreating this pattern. What you see on screen is called a vector field. I will show in a moment how it works. The way it works is that we fill a surface with points and then apply a vector to each of them. And as I said, we have these two sets, 45 degrees, follow the border. Then we use linear interpolation to smoothly blend between these values using this gradient that you see. That's not just because it looks cool, but it actually also is like a mask that, like, the hotter the color is, the closer we get to 45 degrees, the colder the color, the more we follow the shape. And it doesn't only look better, but it's also faster. Because I understand the rules a bit better, it's easier to translate them, and so it's also faster for the computer to calculate. So why did this work? To drive the point home, it worked because of what Anastasia said. Don't mimic the outcome, mimic the underlying phenomena that will get you to the outcome. Which is something I should have done in the first place. So that was more or less it for my talk. I hope I could communicate to you that at the core of making these systems are the rules. And that the better we understand them, the closer we get to a faithful representation. Thank you very much. Yeah, just by the way, you can either ask me some stuff right now, or like I said, if you have any technical questions, you can also come to my workshop and ask me there. And here is my link tree, which has all my links, my Instagram, LinkedIn, my tutorials, whatever. Feel free to check it out.
All right, thank you so much. I imagine there's going to be a lot of board work talk on Christmas Eve this year. Yes. Okay. Questions from the audience? Anyone? By raise of hands. Okay. Thank you.
Hey, Jack.
Hey, quick question regarding starting learning. It's very intimidating. It's very intimidating.
Oh, Houdini. Yeah.
For a lot of people, right?
Yeah.
I guess a lot of people in the talk right now were maybe felt a little bit intimidated. That's why they are not asking questions. But what would you advise someone who sat through this, really wants to do it, and don't know where to start?
The thing is, like, the best advice, like the advice that I know works, but that I hated hearing from programmers is always just get a project, just do it, just and I hate it because it like that's what no one wants to hear, right?
Yeah.
Like that you actually just have to do it. And the thing is, but you shouldn't be afraid about not knowing how it works, because usually we never know how it works. Like every single project, even that, at my job that I get paid for to do, I often don't know how to do it at first.
Yeah.
Being a technical artist often means figuring things out, not knowing things, but learning how to figure things out. And of course, there are a lot of great tutorials. If you've never done Houdini at all, I really recommend you hipflask.how. It's the best tutorials I've known. He really takes you by the hand, step by step, and that made it click for me. I tried it many times, and that one I was like, oh yeah, now I get it.
What is it again? Flix.how?
Hipflask, like
Hip
the
flask.
chemical hipflask.how. Yeah.
Perfect. Thank you so much.
No worries.
More questions? Anyone? I guess everyone's waiting for the workshop.
All right.
Okay.
Oh.
Oh, there's one.
Sure, shoot.
Okay.
I will try my best.
Just about the angling of the big tiles.
The what?
The angling of the big tiles that
angling.
match the overall root shape. Is it based on just like getting the normal onto a packed geometry, or?
Oh, you mean how
Yeah.
they adapt to the ground?
Yeah, I didn't get to that part in my own generator, and I still haven't. So maybe you can give me a tip on that.
That was that's actually the most technical part. That's why I skipped it. Anyone that knows anything about orientations, they share my trauma. No, that's like one of the few things that is actually kind of difficult in 3D is when you want to reliably rotate things, because then maybe you need to learn about matrices, and I feel like maybe I'm scaring people more and more by talking about this, and I should just shut up. But the thing is, like, most of the time you don't need to know about this. Like, that's the thing. Like, you can start Houdini by just doing really easy stuff, and you can make it as complex as you want. But basically, to answer your question, the way I do it is, like, I project them onto the surface with a raycast, what you did in your workshop yesterday, and then I sample the closest surface using XYZ dist and the premuv function, and I can that way figure out where the surface is pointing, and I can then, I think it was with the, I'm using packed primitives, and I'm rotating it using the make transform function, I think.
Right.
I don't
that
fully
sounds
remember.
plausible.
But that's basically it.
Thank you.
Easy.
Easy, right? Just do it. Just.
That's what I would have done.
Yeah, I know, right?
Okay. Well, thank you so much. Everyone, don't forget